Hi everyone, I'm Huayan Tian from the Empathic Computing Lab at the University of South Australia. On behalf of all authors, Gang Li, Huidong Bai, and Mark Biddinghurst, I am presenting our research work using virtual replicas to improve mixed reality remote collaboration. Let's talk about the motivation of our research first. We all know it was difficult and risky for people to travel during the COVID-19 times. But how about if a robot broke down in a factory during that period? Could it be possible for the remote expert to fix the problem remotely and easily as if they were face-to-face with the local user? This situation leads to our research motivation to enable remote collaboration to be more like local collaboration. Driven by this motivation, we reviewed the prior researches on 3D mixed reality remote collaboration and found some gaps. The first gap is that most prior researches reconstructed the whole environment of the task space as a single mesh model. With this approach, it is hard for the remote expert to identify each object in the scene of the virtual environment. And it is also difficult for the remote expert to modify and operate the reconstructed object in a single mesh model. Except for that, we also found no previous research did the comparisons between the virtual replicas manipulation spatial communication queues and the 3D annotation join spatial queues. These research gaps caused two serious problems. The first problem is reconstructing the whole task space as a single 3D mesh model hinders the communication between the local user and the remote expert. The second problem is that join 3D annotation is not expressive enough for the remote expert to deliver his instructions and intentions to the local user rapidly and accurately. In order to fill the research gaps, we put forward two research questions. The first question is, what are the limitations of joint 3D annotation in a 3D mixed reality remote collaboration system? The second question is, could the capability of letting the remote expert manipulate the virtual replicas improve the collaboration between the local user and the remote expert? For answering our research questions, we brought forward two hypotheses. The first hypothesis is joint 3D annotation on the scene would not be efficient enough in performing tasks compared to manipulating virtual replicas. The second hypothesis is manipulation of virtual replicas could improve the overall collaborative experience in a 3D mixed reality remote collaboration system. For proving our hypothesis, we performed a within-subject user study. In this user study, there are two conditions. The first condition is to let the remote expert to draw 3D annotations to deliver his instructions and intentions to the local user. The second condition is to make the remote expert to manipulate the virtual replicas to demo his instructions and intentions to the local user. We recruited 24 participants and organized them into 12 pairs. In our user study, the physical task is to solve Soma cube puzzles. We collected task completion time as the objective data. We used the MEC Spatial Presence Questionnaire, NMM Social Presence Questionnaire, NASA Task Load Index Questionnaire, System Usability Scale Questionnaire to collect the subjective data. We also defined a customized questionnaire for both conditions. We asked some open questions after finishing each session of the experiment. In order to execute our user study, we designed a 3D mixed reality remote collaboration system. In the system, for the remote side, we used 3 depth sensing cameras to capture the local environment of the task space and stitched the 3 captured point cloud models together to form a live model. We also pre-scanned the local environment and reconstructed it as a static single mesh model. We combined these two types of model into a single unity scene and then provided it to the remote expert wearing a VR headset. In the local side, the local user wearing an AR headset can see the task space and the avatar of the remote expert, and he also can see the remote expert manipulating the virtual replicas and drawing 3D annotations. And in our experiment environment, we mounted the 3 Azure Kinect cameras onto the 3 different seating corners. We put the 7 Soma cubes onto the bookshelf and let the local user set up the SOMAcube puzzle solution on the desktop. In the VR side, we integrated the SOMAcube puzzle solution instructions panel into the virtual environment, as well as the SOMAcube's name panel, so that the SOMA remote expert can use these two panels to communicate with the local user. This picture tells how the experiment of the virtual replicas manipulation condition was performed in the experiment of our user study. This slide is about how the experiment of the 3D annotation join condition was conducted. Now let's watch a short video about how we conducted our user study. The video you are seeing is about the virtual replica manipulation condition. From the video, you can see that the remote expert was manipulating the virtual replicas to demo to the local user about how to set up the SOMAcube puzzle solution. This part you are watching is about the 3D annotation join condition. From the video, you can see that the remote expert is joining 3D line annotations to tell the local user how to finish the SOMAcube solution. Now let's have a look at our result. From this slide, we can see that the virtual replica manipulation communication queues took significantly less time than the 3D annotation join spatial queues. In terms of the NMM social presence questionnaire score, the virtual replicas manipulation spatial queues got a significantly higher score index than the 3D annotation join queues. As for the NASA task load index, the replica manipulation got a significantly lower physical and mental effort index. For the system usability, the virtual replica manipulation spatial queues had a significantly higher score index than the 3D annotation join spatial queues. From the result of the preference ranking question answers, we can see that most participants rated the virtual replica manipulation communication queues with higher score. 23 of the local user role participants gave their preference to the replica manipulation spatial communication queues, and 20 of the remote expert role participants chose the virtual replica manipulation spatial queues as their favorite communication queues. Altogether, our user study result indicated that the virtual replica manipulation spatial communication queues actually improved the mixed reality remote collaboration, and most participants gave a high rating to the virtual replica manipulation spatial queues. From the findings and the feedback of the interviews, we derived the following implications. The virtual replica manipulation is more expressive than 3D annotation join. We should promote the usage of the virtual replica manipulation in the design and implementation of the 3D mixed reality remote collaboration system. Besides, we should also try best using the wireframe style object model as the virtual replicas instead of using the solid mesh style object model. These implications lead to our future work. We will continue to explore more use cases with the virtual replicas manipulation as the spatial communication queues. We will change the one-way virtual replica manipulation to two-way so that both the local user and the remote expert can operate the virtual replicas. We will also try to change the virtual replicas from the solid mesh style object model to the wireframe style object model. Furthermore, we also plan to apply computer vision to do the site alignment among the live point cloud models and the reconstructed static models. And we'd like to apply machine learning techniques to do the foreground manipulable object segmentation for our system. That's all for our research. Thank you for your attention. At the end, I'd like to thank the University of South Australia for funding our research.